So yeah, that's what we're doing today. We're going to try to implement a JSON parser in Haskell from scratch. No third-party dependencies, absolutely no third-party dependencies, only base. Only base, which is the standard library of Haskell. As many of you know, if you program the Haskell a little bit. And yeah, and it's going to be extremely small. Surprisingly, you will be surprised how easy it is. Well, relatively easy to implement a JSON parser and how to implement parsers in general in Haskell. And it's no surprise that there is a lot of compilers and parsers implemented in Haskell because how easy it is to do that. How was the idea born? The idea was born on the bot development stream. And as a matter of fact, we implemented a parser of the DSL for custom commands on the stream for the bot. So I decided to take that idea and apply it, you know, to something that majority of people are familiar with. For example, JSON parser. Can we implement a JSON parser using the same technique? And I was experimenting with that, and it turned out, yes, we can. And I was actually surprised how easy it is. Like, yeah, you can just implement a JSON parser using the same technique. And the technique, for those who don't know, is called parser combinators. Usually when people use parser combinators in Haskell, they use third-party dependency like parsec, like, you know, third-party implementation of parser combinators. But it turns out it's not that difficult to implement your own. Maybe a little bit slow, maybe a little bit not complete, but still parser combinators that can get the job done and make you not depend on a third-party dependency, which will increase maintainability of your code because, first of all, that dependency is way smaller than whatever you're gonna take from Hackage, and second of all, you're gonna have a full control of it, meaning that if you want to make some changes, you don't have to contribute them to the main developers. You don't have to go through the review process. You don't have to do anything. You just make the changes, and they already in your source code. Maintainability only improves. But anyway, it depends on what you need. If you need speed, you probably have to use like a third-party dependency. Let's get started. So let's start the project. Let's see how we can do all of that. I'm gonna go and create a folder in programming sorting, and let's call it Haskell JSON. So this is where we're gonna put all of that, and I'm gonna go to that folder as well. So we are inside of the folder. There's nothing there. You see it's empty, total 0. There's nothing there whatsoever. I'm going to start Emacs from within that folder. I'm gonna split everything in half. And I'm gonna start GHCI main.hs, excuse me. So this file does not exist. I think we need to first create it and save it. And on top of that, let's actually put this thing here and align everything. Yeah. And another thing that I really want to do is to start GHCID process, which will, yeah, this is how you go to the directory, of course, which will constantly recompile. It's like compilation and recompilation, compilate, which will constantly compile this module. So the module, as far as I know, has to be a main module. Yes, and it also usually should contain some kind of an entry point. So I'm gonna just put it here just in case, so GHC won't complain and everything is okay. So if you don't know what are those tools, I really recommend you to check out my Haskell setup video. You can find it in the chat. And let's get started. Let's try to define some kind of AST for our JSON, right? AST stands for abstract syntax tree, and this is what we need to define. So let's go ahead and do data JSON value. So what we're doing, we're trying to parse a JSON value. So what is a JSON value? First value, the most simplest one, I suppose, is JSON null, because null is a part of a JSON. As far as I know, you can have a null values. The second value the second kind of value, I would say, is a JSON Boolean. So let's create a constructor JSON Bool that encapsulates a Boolean type of Haskell, right? So what other types a Boolean has? What do you guys think? What do you guys think? Well, JSON also has numbers. As a matter of fact, I think it has a majority of types of JavaScript. Yes. I think it has all of the types of JavaScript, basic types, I would say. Undefined. Does it have undefined? I'm not sure about that. Probably doesn't have undefined, but it does have null. But we're not going to go with undefined today. Maybe if it does contain undefined, it should be that difficult to actually add undefined to our parser. JSON string, yeah. So you guys are right. So there's also JSON strings. JSON string, which will encapsulate a string, of course. And what's interesting about number, let's actually simplify ourselves our life, and support only integers, okay? Because it will be just easier to work with them, because you only have to like parse digits. So we're gonna put a note that no support for floats, okay? No support for floats. All of this code is going to be published on GitHub, so feel free to submit a pull request if you want to change that, if you want to improve the parser. And yeah, feel free to add support for floating point numbers. Another thing is going to be probably JSON array. So this is another like a basic type of JSON. And what's interesting is that with this constructor, JSON value finally becomes recursive. You see, JSON array is a list of JSON values. So this is where the type becomes recursive. So it basically refers to itself. And the last value is probably going to be JSON object. So ideally, it has to be a map that takes a string as a key and returns a JSON value as a value. But map is a third-party dependencies, unfortunately. In Haskell, in standard library of Haskell, there is no maps at all. They are located in a package called containers. And in this particular case, in Haskell, by map, I probably mean the following type. This one, which is located in package containers, but we are not allowed to use that, boys and girls. We're not allowed to use that. So yeah, this is a map. Implementation, it has the following operations. Probably the most interesting part is located somewhere in strict, somewhere here, but we're not allowed to use that because it's not part of the base. As far as I know, it used to be part of the base. As far as I know, it used to be, but no, it's not anymore. So as far as I know, we only have these 6 basic types. We have only these 6 basic types, and of course, to actually make an object something else, yeah, I'm sorry. Since we're not allowed to use this, instead of using map, we're gonna use a list of pairs, string JSON value. So this is how we're gonna implement associative array. So it's gonna be basically a list. It's not going to be fast. For example, looking up in such a list is probably going to be n, but again, feel free to submit a pull request to this code when I will finally release it. Feel free to submit a pull request and improve it. And once I release this code, I think I'm going to be okay with people using third-party dependencies. Yeah. Basically to make this entire implementation better. The only reason why we use these kind of stupid decisions is because we're limited in what we can use, because it's a challenge. It's a challenge. Everybody likes challenges. Anyways, okay. So we defined our AST type, but I also want to derive interfaces like show and equal. So basically, show is needed, so I can just take JSON number, type it in REPL, and REPL will print me back, because now REPL knows how to show it. Without this thing, it won't be possible at all. It will say that, I'm sorry, I don't know how to print it. But once it implements show, you can actually print it. You see, so this is, yeah. If you want to print, if you want to make your value printable, you have to work for it. You cannot just define a type. You have to work for it. You have to type these 4 letters, otherwise nothing's going to work. An equal is probably needed so I can compare the values of this JSON stuff. Okay, so we define AST. Now let's define our parser. So what I want to do, I want to create separate small parsers that are capable of parsing each and individual type of JSON. Right, and then I will want to be able to combine those parsers together into a bigger parser that can parse the whole JSON. So it's kind of similar to recursive descent, I think. It's kind of similar to recursive descent, but it's really not. Maybe it is. It depends. So in that particular situation, what's going to be the parser? What's going to be the parser? Well, parser is supposed to take a string and return the value that we want to parse, JSON value. Well, generally, parser may return anything, whatever we want to parse. Like it takes a string and returns whatever we want to parse. But since parser can parse only one specific thing, that means there's some input left for further parsers to parse. Right, so this parser should not just return the value it's parsed, it also should return the rest of the input for other parsers, so we can combine them together. So you see, parser is already not a function from string to the thing we are parsing, right? It's no longer a string to a thing. It's a string to a pair the rest of the input and the thing that parser is capable to parse, so we can chain several parsers together. So this particular approach makes the parsers composable into chains. Isn't it cool? I think it's pretty cool. But that's not it. What if the parser cannot parse the thing it's supposed to parse? What if it cannot? So we need a way to indicate that the parsing has failed. Maybe. So it complains about compilation because it's not implemented. Maybe we can actually suppress the compilation error with something like that. So which complicates the thing a little bit. So you see, parser becomes more and more complex. But what if we want to know exactly what happened? What we want to know exactly what happened, we're probably going to use something like either, which will tell us like exactly what happened. For example, some unknown character encountered, or end of file in character, end of input, I would rather say. So you see, type becomes even more complex. But what if we want to know where exactly that happened? So the type will become even more complex. So because it will contain the place where that thing happened. And what's going to be the place? I don't know, we can use just a character in the input, but it will be more convenient for people to have, you know, also a line. So you see, parser is not a simple thing. You may think that parser is just a function from string to A, but it's actually this monstrosity that you have to manage. And managing complexity is actually a very strong side of Haskell. So, but if we're gonna try to manage this kind of complexity, I think we're gonna, you know, spend like the whole stream coming up with proper abstractions. So I think I'm gonna go back a little bit and still use maybe. For this particular stream, we're gonna use only maybe for indicating errors. We're not gonna print the exact place and the exact situation what happened. We're gonna just use maybe. If it returned nothing, that means parsing failed. If it returned just, that means it was successful. I'm gonna put a note that no proper error reporting. So, and again, I'm going to publish this code, and feel free to actually, you know, do some kind of an exercise and try to add like a better error reporting for this particular parser. Okay, so this is how our parser will look like. But we want to actually have it as a type. We want to reason about parser as an object, as some kind of a type. So let's create a type called parser, which is parameterized by the thing it parses, and its definition is going to be this. So here we go. We created a new type called parser A. So, and for example, JSON parser, like JSON value, is going to have this particular definition. So you see, it's a parser that is capable to parse JSON. So we basically hid this entire complexity under this particular type. But this is just a type synonym. This is just a type synonym. So that means that this type and this type are indistinguishable from the point of Haskell compiler. They are the same type. It's a type def of Haskell. In this particular situation, Haskellers, epic Haskellers, usually create a new type. And a new type is supposed to be a type that has only one data constructor that wraps only one single type. We're going to use a record for this particular situation that contains only one field, which is called run parser. So record in Haskell is basically sort of like a data structure, like a structure struct in C. And this particular struct contains only one field, which is called run parser. And the type of that field is this function. Why did I decide to call the field of a structure run parser? Well, when you define a record, when you define a structure in Haskell for each individual field, Haskell creates a function that is capable of extracting that value from a structure. It's a very interesting thing. If you take a look at it, we defined parser as a function from string to maybe, but if you look at the type of the parser, it's a function from parser, string, and maybe. You see, for each field of the record, Haskell generates you a function with the same name as the field, which is capable of extracting that field from that structure. Which means that if you have a parser, for example, JSON value, you can apply run parser to it and it will give you the type of the parser itself. And then you can continue applying things to it, and then you will get the actual value using currying and stuff like that. So you see, it's sort of like a trick. This is supposed to be a field of a record, but since Haskell generates functions for a field, we can trick it to generate a function and have it like a readable name. Does it make any sense? What's funny is that it's such a common pattern in Haskell that you will see it pretty much everywhere. Pretty much everywhere somebody creates a new type, they will always create a single field called run something or to something and so on and so forth. So in Haskell, people give like a very actionable name for fields of the structure because Haskell generates functions for those fields. Does it make any sense? Like, it didn't make sense for me at first. I actually was looking into that. I actually pondered like very long at this kind of code, and I couldn't understand it. But now I finally understand it, and yeah, it's kind of strange. I think we could have like a little bit better syntax for that, a little bit more intuitive syntax for that. But it is what it is, and it isn't what it isn't. But what's important is that now I can take some kind of a function that takes, you know, string and returns something and easily wrap it into a parser. And then at any point I can unwrap it from a parser by running it. And yeah, that's what it does. So basically, if you want to wrap a function into a parser, you use this thing. If you want to unwrap, you use this thing. Very strange, but Haskell is strange in general. We have everything in place to start implementing a parser. Let's actually go through all of these types, and for each type implement a separate parser. For JSON value, we're also gonna have a JSONMu parser. So how can we parse null? What do you guys think? How can we parse null? So we need to implement a parser that is capable of parsing just a small, simple part of JSON, just a sequence of character NULL. How can you do that? It's very interesting because to be able to parse a sequence of characters, we need to be able to parse a single character. How can we parse a single character? Let's implement a helper parser called Charpy, which parses a single character. So But what character this parser is supposed to parse? Well, let's parameterize this function with the character that it's supposed to parse, and we'll return as a parser that parses that character. Okay, so what we're gonna put here? So what are we expected to even have here? So I'm gonna put a hole here. So there's a very interesting feature in Haskell. It's called holes. So basically you put somewhere where an expression is expected the following name, underscore, and some arbitrary suffix, whatever you want. And that will be treated as some kind of hole. And then the compiler will tell you what is expected type of the hole. You see, I put this hole here, and the compiler tells me, well, the type of the hole is supposed to be this thing. And furthermore, it will tell you the surroundings of the hole, meaning that you have at your disposal variable x that has type character. Right, and we do have, x, which is a character. So, and you're gonna have like a several relevant bindings here, and you'll have to compose this expression from these relevant bindings. So this is a really cool feature in Haskell that helps you that guides you through the implementation. So since we know that it's supposed to be a parser, we can wrap our hole in parser. So now hole has a type of function from string to maybe, and relevant bindings actually grew. Now we can actually put more things in here, but since we know it's supposed to be a function, I'm gonna wrap all of that into a function and adding the input, and now we expect maybe string character, and the relevant bindings are input, x, and the function itself in case we want to do that recursively. All right. So we need to be able to parse a particular character. So to do that, we actually need to pattern match the input and extract one character from it. So how we can do that? I'm going to do case input. And what are possibilities here? We may have some character y and the rest of the input. Maybe we're going to call it y's. And another possibility here is that the input is empty. And what we're going to do in this particular situation. So in here we have to return maybe, but I think in case of empty input we can just return nothing. Here we have to return something only if that character is equal to the expected character. If we actually found the character here, what we have to do? We have to return the parsed value. The parser value we expect is a character, so meaning that is going to be the character itself, and the rest of the input. What is the rest of the input? Well, it's y's. And on top of that, we have to return just to indicate that it was parsed successfully. Well, this case, we can actually generalize this case, so it covers not only empty input, but also when y and x are not equal to each other. And after that, we may want to try to format all of that, and this is the formatting. And there you go, it actually compiles. We have a parser that is capable of parsing a single character. Would you look at that, boys and girls? Would you look at that? So, Charpy, and let's take a look at the type. It's a parser character. Let's try to run this parser. And what kind of type do we get from it? We get a string from function from string to maybe. So if we apply something like h to that parser, nothing will happen. I wonder why. Oh, because it's supposed to be, yeah, I'm sorry, it's supposed to be input, which is a string. Let's apply hello to it. And there's nothing. Why there is nothing? Why, when we apply character that is capable of parsing only n to hello, it says nothing? Because there is no n as a first character. What if we put nice here? It parsed it. As a result of the parsing, it returned n, exactly what would we expect to parse, and the rest of the input that is unparsed input, it returned ice. So, and that ice can be used for the next parser in the chain to continue parsing of a bigger expression. That's the point of it all. I think we can even simplify all of that. Well, I think we can even simplify. So you see, this function can be put under where. Boomer jokes, by the way. Like that. So it's a little bit easier to work with. So you see, we're not using lambda, we're using where expression. It doesn't really work properly. I wonder why. Probably I have to reformat everything. And formatting in Haskell is actually quite difficult, if you ask me. Yes, something like that. So hopefully it will work now, and if we rebuild it, everything works. Furthermore, pattern matching can be done on the level of a function. That means that I can take that case and implement it in the following way. So I can probably just remove this stuff and say f this otherwise equal Jas, and it still works. So I think syntactically this is a little bit better, because the argument is f is destructurized as the head and tail. Then we have condition guards, which are conditioned that the head of the input is equal to the expected character, and we return parsed result. And otherwise, in any other case, it doesn't matter what it is, empty input or I think in the case of empty input, we'll have to actually, process it directly anyway. Yeah, I think we'll have to process it directly anyway. Yes. Yeah. And it's supposed to still work. So we have nice. If it's empty input, it's still going to be nothing. So, but I think syntactically, just visually, it's just a little bit better than the mess of lambdas and stuff like that. So now we know how to parse a single character, but our goal is to parse a sequence of characters. And this is something interesting. So we want to create a parser very similar to Charpy, but it parses a sequence of characters. So we provide a sequence of characters as a parameter of that parser, and it returns a parser that parses a sequence of characters. Nice. So what we can do? What we want to parse? We want to parse string null. String, I'm not sure if we can info this thing. I think you cannot yet. String is a list of characters. That means I can take the list of characters and map it with Charpy. And you can print it. Let's take a look at it. Like it actually succeeded, but you cannot print the parser because it's a function. Functions are not really printable from the REPL point of view. And we got a list of parsers. But what we want to have, in fact, is a parser of a list, right? Because we want a single parser, we want to have a single parser that returns you a sequence of characters, but we only have a sequence of parsers. What can we do about that? I can see already in the chat somebody got the idea of what we want to do. Yes. Somebody already understands where all of that leads. There's a very interesting operation. So you see, the basic idea is here is what we have two parameterized type. First parameterized type is a list. It parameterized by the elements it contains. And the second one is parser, which is parameterized by the element it parses. We want to turn them inside out. Instead of list of parsers, we want to have parser of lists. That's right. So we have in Haskell, we have a very interesting operation, which is called sequence A. It works with two types. It works with applicative. It's not a really good type, to be fair. But in any case, T is traversable and F is applicative. Don't try to understand what it is. It's just two different interfaces, just like list and parser. It takes traversable of applicatives and returns you applicative of traversable. It turns this type inside out. Well, this is traversable. We know for sure that list is traversable. So the only thing we need is parser to be applicative. But parser is nothing. It does not implement any kind of interfaces. We need to prove that parser is applicative, and that magical operation will just work, and it will magically implement string p. As a matter of fact, the implementation of this thing is going to be straight up sequence a Charpy, and if we try to compile that, it will say very interesting thing. I wonder, oh yeah, the idea is going to be the following. We'll have to map the input with Charpy, and then we'll have to apply the sequence a to it, and it will say that there's no instance applicative for the parser, so you're not allowed to use that magical operation yet. We just need to prove to the compiler that parser is applicative. We just need to prove that. Furthermore, this particular thing can be reduced, meaning that I can turn it into point-free notation by adding a bunch of dots, and it's going to be equivalent. So what's interesting is that, let's take a look at the applicative. Let's take a look at the applicative. To prove that something is applicative, first thing we have to do is to wait until this simple page loads up. It loaded up. The second thing we need to do, we need to prove that the same type is functor. The same type is a functor. So first thing, we need to prove that it's a functor, and only then we should be able to prove that it's applicative. A functor is a little bit simpler type. Let's take a look at it. So the only thing it supports is this fmap operation. I like to call this operation a penetration operation. So what it basically does, it takes a function that takes a and a functor that contains a, and it allows you to take that function and inject it into that functor, and as a result you get the result of this function wrapped into the same functor. So it penetrates the functor with your function, penetration operation. That's right. So we need to prove that parser is penetratable, meaning that if I have a parser int, I should be able to increment whatever is inside of it. It's not a real Haskell code, but it's basically the idea. So you have a parser int, and I want to be able to fmap it with +1, and it will increment that number inside of the parser. So I should be able to penetrate my parser. So how can we do that? Let's go back to the parser and try to implement an instance of a functor for the parser. So it will not shut up about not implemented thing here, so I probably want to comment it out for the time. Okay, so you see it says that there is no fmap. So in fmap we expect function f and parser p. Let's see what we are expected to return. So we expected to return the parser, and we have p and f. So let's unwrap the parser. So as you can see, p right now is a parser, which is kind of useless. We pattern matching, unwrapping it, and let's take a look here. So now we have p as a string. And we have function that takes a, but a is down here. So we need a way to access that a and penetrate f into it. Something like that. So whole right now is expected to be a parser b, which is not really useful as well. So this thing I'm going to do, I'm going to unwrap it as well, where f is a and f is supposed to take an input. So let's take a look what we have here. So now it doesn't really have any type. God damn. Not really convenient. What if we use like lambdas and stuff? Will it be a little bit easier to work? Yeah, okay, I don't know why I didn't understand the where part, but whatever. So underscore a is supposed to be maybe, and what we have at our disposal, we have the input, the function that is capable of consuming that input, and the function that we're supposed to penetrate to the result of this function. Quite interesting. And we're supposed to return maybe. So maybe is a monad. That means I can use a do notation here. So I take P and apply input to it. And what I get is a maybe that returns the next input, the rest of the input after that parsing, and some kind of a value X. And what we're supposed to return here. So we're supposed to return a string and B, but what we have at our disposal is X, which is equal to A, and somewhere down below, I'm not sure if it's visible, it's not going to be visible, we have F that accepts A. So that means we just penetrated deep enough to have an access to A. You see, we actually got an access to A, and this is exactly the value to which we have to apply function F to. And what we do, we just apply function F to it, and then return the rest of the input, wrapped into just indicating that everything went okay. And we just proved that the parser is, in fact, a functor. What that means is that if you have a parser, for example, that is capable of parsing character A, you can fmap that parser, for example, with function ord. So ord is not available here right now. I have to import data.char. Data.char is part of the standard library. We are allowed to use that. We are allowed to use that. I'm not cheating here whatsoever. So ord, it takes a character and returns an integer. So if I put X here, it will return ASCII code of that character. So if I have a parser that is capable of parsing like character N, then I penetrate it with ord, I'll get a parser that parses int. So this parser will not only parse N, it will automatically convert it to ASCII code of N. So, and I can easily demonstrate how it works. I can easily demonstrate how it works by running that parser on sequence of characters. Nice. So you see, instead of N, it returned 110 and the rest of the input as ice. And if you check the ASCII code of N, it's 110. So it not just parses the single character, it automatically converts it to a number, so you can do something with it, and you can actually change those transformations on the parser, and it will do that automatically after it's done parsing. So that's what it means for a type to be a functor. You're now able to penetrate a value inside of the functor, so it's easier for you to work with it. But that's not enough. It's only one step in proving that parser is also applicative. And applicative is a little bit more difficult to prove, but not much. Instead of a single operation, we'll have to implement two operators. Minimal implementation for applicative is pure, and either this operator or this operator. But as far as I know, it's defined in GHC base, so we're going to focus only this operation. So the first operation we'll have to implement is pure operation. This operation is supposed to take value A and return you an applicative that contains that A. So basically, it's just supposed to construct a parser that ignores the input and always returns the value that we told it to return. That's it. So this is what pure operation is supposed to do. Instance applicative parser. By the way, you cannot do this thing if you didn't do this thing. Seriously. Even if you implement both of the applicative operators correctly, they won't work because you didn't prove that parser is also a functor, because those operations don't make any sense if it's not a functor. Okay, so first thing is going to be pure. We're going to take a parser and what we're supposed to return. Well, as I already said, we're supposed to return. This one has to be an X, by the way. We're supposed to return a parser that ignores its input and returns that value. But to properly ignore that input, we're going to actually, forward it like that. And yeah, of course, you also have to wrap it into maybe. Cool. So as far as I know, now you should be able to do things like that. No instance applicative parser. Oh, I cannot use it. Yeah, it's not fully implemented, but soon I will be able to do things like that. I will be able to construct a parser that ignores the input, but always returns that value. Okay, so this is the first thing. The second operation that we have to implement is this weird operation. Let's take a look at the type of it. It takes a function from A to B wrapped into applicative. And then we take applicative that contains A, the input of this function, and it returns applicative that contains B, the output of this function. You know what's interesting? It kind of reminds me of fmap. The only difference between this operation and fmap is that in fmap, the input function is not wrapped into the functor, but here it is actually wrapped into it. It's kind of interesting, like, why would you use this particular operation? So I don't know what's the official way of using that operation, but I use it the following way. Imagine that I have two applicatives. By the way, maybe is an applicative. So you can actually use that operation on maybe. So imagine that I have two maybes that contain, let's say, 5, and another one contains 6. I want to sum them up. But I don't want to unwrap them. So what I do, for example, I have operation that sums up two numbers, plus. I can take the first value and penetrate it using fmap. By the way, I forgot to mention that this operation is actually synonym to fmap. So I'm going to use this and this interchangeably. So I'm penetrated with just plus, but this is not enough. Because of the carrying, I now have maybe that contains a function. And that enables me to use this operation, because here you also have applicative that contains a function. So that means you can continue chain with this operator. And that will sum up these two numbers without unwrapping anything. So you see, you use initial penetration and then you use like a deeper penetration to perform even more operations inside of the applicatives. So something like that. This is how you usually use it. And what's interesting is that it actually scales. For example, imagine that you have a function that takes, let's say, 4 arguments. This is a function that constructs a tuple of 4 elements. What you can do, you can take this function, penetrate the first element, then continue penetrating deeper the second element, then even deeper the third element, and the most deepest fourth element. And it will penetrate all of the layers of applicatives and construct you a single applicative with 4 elements. So you see how it scales. So as far as I can understand, this is exactly the use case of this operation. And to be called applicative, the type has to support that operation. So there we go. Let's implement it. So what do we expect here? Oh, come on. So we have first parser that contains a function, second parser that contains the argument of the function, and we are supposed to return result. Let's actually unwrap all of that. So we work with specific functions. So parser that also accepts input. So what we have now? We have an input that takes a string, 2 functions that also accept strings, and we need to return maybe, the parsed thing. Okay, so we're gonna use maybe as a monad, meaning that we have to take the input and put it through the first parser. We put it through the first parser, and what you get maybe the rest of the input and argument. No, we're working with this one. The rest of the input and the function that we have to apply to the argument here. So we're going to quickly destructurize it. So this is the partial input and value A, something like that. Okay, so after that, we need to take this input and forward it through second parser. And that will give us even more partial input, and the function that we're supposed to apply to A. That's it. We actually got all of the components that we need, and now we just need to return just to indicate that it was successful the rest of the input and the result of A applied to in the result of F applied to A. I think this has to be it, but not really. I think I forgot something here. What did I forget? What did I forget? The first thing is supposed to be function, and the second thing is supposed to be the argument, and now it compiles. So, speaking of chaining several parsers together, right? Chaining several parsers together. To chain two parsers together, what you have to do, you have to take an input, put it through the parser, and receive this maybe. This maybe can be just or nothing. In case of the nothing, you have to break the whole chain of the parsers and forget about it. In case of just, you have to extract that pair, save that output, take the next input and put it through the next parser and repeat that operation over and over again. Well, this particular implementation does exactly that. We have two parsers and we need to chain them together. So you see, first parser returns you a function, so you take the input and you receive the next input, right? And since we are inside of a maybe monad, we use do notation, so we don't care if it breaks or not because it will break automatically. Then we take that input and put it to the next parser. Then we take that input and return it, so you can chain even more. So this operation does exactly chaining of the parsers. So this is where chaining actually happens. Okay. So after that, we actually proved that the parser is applicative. It supports penetration operation, pure operation, and double penetration operation. So it supports all of the operations to be called applicative. Parser is applicative, and we proved that live on stream, and that was caught on camera. We have a proof that parser is applicative. That's right. Anyways, so what that means? That means we can actually use sequence operator on this thing. So again, you have a null, you map it with Charpy, you get a list of parsers, and you sequence A them. And you sequence A them, and what you get? Parser of list. See, it actually worked. We can now turn these types inside out. We can actually turn these types inside out. So now we officially have implementation of *p parser that can parse not just a single character, but a sequence of character automatically, just because parser is an applicative. So now, if we reboot that, we can try to do something like null. It gives us a parser that parses string, and let's run this parser and apply hello to it, and it failed. But if we apply null to it, it returned null, and the rest of the input is empty because it consumed all of them. If we add more characters to it, it will not touch them, and it will only parse the chunk that it's supposed to parse. If we don't provide enough, it will fail. You have to provide at least this sequence of characters that you put here. We now know how to parse a sequence of characters. How about that? How about that? So, how can we now implement JSON value? Well, not JSON value, I'm sorry, JSON null. So we need to parse sequence of character null. But this parser returns JSON value, but we return characters. How can we turn this into parser that returns JSON null? Well, as I already mentioned, parser is a functor, which means I can easily penetrate it and replace the value inside of it. This is why we implemented a functor interface. Look at that. We ignore whatever the fuck is inside of the parser, and we replace it with JSON null. And it doesn't compile. because I'm actually doing that in the wrong place. I'm sorry. I was so I was so excited about this that I actually put it in the wrong place. This is where we have to do that. Yes, this is where, and it works. See, we you know, just ignore what's inside of the parser and we return null. So now if you try to run parser JSON value, JSON null, I'm sorry, and you try to parse hello, it will return nothing. But if you try to do null, it will not return you a string null. It will straight up return you JSON null, which is a data constructor of a JSON value. How about that? We actually managed to parse JSON null. Now, since we know how to parse null, let's parse the next value. Let's parse JSON Boolean. Well, parsing JSON Boolean is actually a little bit more complicated. Just a little bit, just slightly. JSON parser, JSON value. Because in case of a JSON Boolean, it's not enough to parse one sequence of characters. We need to be able to parse two different sequences of characters, because Boolean is either true or false. So what we need to make our parser to do is to try to parse this sequence of characters, and if you cannot do that, tries to parse this sequence of characters. So we're gonna have two different parsers, and we need to combine them into a single parser that just tries these two parsers in sequence and picks the one that is successful. What's funny is that there is an interface for that. It's called alternative. And to access that interface, I think you have to actually import control applicative, if I'm not mistaken. So let's take a look. Alternative. There we go. So to be alternative, you have to be applicative. So to prove that you're alternative, you need to be applicative. Our parser is already applicative, so we already satisfied that step. But what kind of operations you have? The most interesting operation is this one. It takes alternative away and the second alternative away and returns alternative away. So let's take a look at maybe. Maybe is alternative, so it will work. This operation will work on alternative. So let's do the following thing. What will happen if we apply this operation to these two maybes? It returns the first one. Why does it return the first one? Very interesting. What if the first one was actually nothing? It returns the second one. What if both of them were nothing? It returns nothing. What does this thing do? What does this thing do? If you take a look at the alternative, it also has a notion of an empty alternative. What this thing does, it picks the first non-empty alternative. For example, in case of a monad, maybe, I'm sorry, in case of a maybe, an empty maybe is nothing. So this is exactly what we need to do. In our case, an empty alternative for the parser will be failed parser. That's right. It's going to be a failed parser. And that will help us to actually implement the Boolean parser, because if parser was alternative, we could do something like that, and it will just pick the one that did not fail, right? So it will basically try this one. If it's failing, that means it's empty alternative. It will try this one, and if it does not fail, it will actually pick it up. So let's try to prove that parser is also an alternative. So yeah, you have to import data alter applicative. There we go. Not data control. Naming schema in Haskell is beautiful. It's so easy to remember. So we need to implement what? Alternative. We need to first implement the empty value for our parser. What will be an empty value for our parser? Well, it's going to be parser that fails. How can you implement a parser that fails? It's super easy. You just fail. That's it. So you ignore your input. You just ignore your input and you just fail. This is how you implement empty. Now we need to implement this magical alternative operation. So we're going to take two parsers and we are supposed to return something. So what we are supposed to return? Well, we're supposed to return a parser. Again, let's unwrap everything. Let's unwrap everything and let's take a look at what we have in our environment. So we expect an input. Okay. So what do we have? We have two functions that consume input. We have input itself, and we have to return maybe. So what's fun is that maybe is already alternative, as we already demonstrated. Maybe is already alternative. Maybe we can take advantage of that. So we don't have to implement everything to support alternative. We just need to utilize the alternative implementation specifically for maybe. So what we're going to do? We're going to take P1 and apply an input to it, and we get a maybe. Then, if that maybe fails, we take the same input and apply it to the second one. And then this will automatically choose the one that is not failing. And as far as I know, this is the whole implementation. Seriously, I'm not even joking. This is the whole implementation. So we basically implemented a proxy to the alternative implementation of maybe inside of the parser, and it will just work. Something like that. What we're doing here logically, we take the input, we put input into the first parser, trying to parse that. If it fails, we put the same input to the second one and trying to parse that. And this is how we choose between these two parsers. So now to implement JSON Boolean, we need to just choose between true or false. But it's going to fail. It's going to fail because the resulting parser returns the sequence of characters instead of JSON value. So we need to penetrate this parser and transform it into a JSON value. But this time it's going to be a little bit more complex because depending on what is actually inside of the parser, true or false, we have to return different things. So what should we return? In case of sequence of characters true, we have to return JSON bool true. In case of false, we have to return JSON bool false. And what's funny is that potentially this particular pattern matching is not exhaustive. We don't check all of the possible variants. Potentially there can be something else, but if we implemented everything correctly, there should be nothing. So I'm gonna just mark this one as undefined. And if something goes wrong, it will just fail the application, but this should never happen, by the way. The long and painful troubleshooting starts with the phrase, "This should never happen." Yes. If you ever see this kind of comment in the code you're working with, never trust it. Trust me. Just never trust it. If something can happen, it will always happen. This is Haskell. Can't you prove that it will never happen? Well, Haskell is pretty powerful, but it's not that powerful. I think in this particular situation, you need something that supports dependent types like Agda or Idris. I think those languages with dependent types are actually capable of proving something like that, but I'm not 100% sure. So anyway, so we have a parser that is capable of parsing Boolean. How about that? Run parser. Let's try to parse hello. And there is no JSON Boolean because I forgot to reload my parser. One more time. So you see, you cannot parse hello as Boolean. But if we provide true, look at that. JSON Boolean true. false, JSON Boolean false. We implemented a Boolean parser. What's funny is that we already have two parsers, JSON null and JSON Boolean. What if we combine them together into a more powerful parser? So what that parser will be able to do? Will that parser be able to parse null? It will. Will that parser be able to parse true? It will. Will that parser to be able to parse false? It will. So you think this alternative applicative thing is, you know, academic bullshit that is not applicable in the real world, but in fact, it creates a very powerful abstraction that lets you just express very powerful parsers very quickly. You just implement small parsers and you combine them together into more powerful parser. And furthermore, so we have a function JSON value. Let's actually take this thing and put it into the JSON value. And as soon as we implement a new parser, we're gonna just put it into the JSON value. So we're gonna slowly grow our JSON value parser into a full JSON parser. So yeah, how about that? Now that's what I call an epic Haskell development. So anyway, what's the next one? The next one is JSON number. We need to parse integer. Okay, let's implement that. Excuse me. JSON number, parser, JSON value. So what we have to implement in case of JSON number? In case of integers, we just need to parse a sequence of characters as well. But we cannot use string p in this particular situation. Right? String p, because you have to know exactly what sequence of characters you're working with. In this case, we don't know specific characters, we know the class of the characters. Class of the characters, digits, right? So we need a function that would be able to create a parser that parses the sequence of characters based on some kind of criteria. So you see, it will parse the character as long as this predicate holds. As long as this predicate holds. So in standard library of Haskell, in fact, there's a very interesting function called span. It takes a list and some predicate, and then it splits that list into two lists. Let me demonstrate you. So if you have a sequence of digits and you say span, not spam, I'm sorry, span is digit, it will give you two lists. List of digits and the rest of the input. So basically it consumes these characters until that predicate holds, and it gives you the prefix for which this predicate is true, and then the rest of the input. So we need something like that, but for parsers. So let's try to implement something like that for parsers. So I would like to call this particular function something like span p, right? So it's gonna act like a, you know, span p, and maybe in this particular case it's gonna be a little bit more abstract. So it's going to be a parser that supposed to return a list of things, and it can accept a predicate that works on those things. Something like that. So yeah, let's try to implement that. How we would implement that? So we have a predicate, this function f, and we supposed to provide some kind of a parser. So let us see what we have here. So we have to return maybe a string. We have fa. And we have an input. What's funny is that we cannot make it abstract. We cannot make it abstract because the input that parser works on is actually very specific. It's a string, so we have to actually make it like that. I was hoping that we can make it abstract, but in fact we have to make it specific for characters. You have to make it specific for characters. So here we have an input which is a string. And what's interesting is that what we have to do now, we have to just apply spanf input, and that will split the string. It will split the input exactly as we expected. Basically, the first thing is going to be the token that we're trying to parse, and the second value is going to be the rest of the input that we have to pass on to the next parser. Right, and then we just have to return the rest of the input and the token. This is the whole implementation, believe it or not. So now we should be able to construct this following parser that will probably work if I rebuild, if I reload my REPL. So you see, we have a parser that parses that sequence of characters and then leaves the rest of the input for the next parsers. So now we can quite easily implement the JSON number parser as spanp is digit, but we cannot implement it like that because spanp is digit returns a sequence of characters, but we expect JSON value. So that means we'll have to penetrate that thing one more time and see what we have here. So here we will expect digits. And those digits, how can you convert digits into an integer? Well, you can use something like read. It will automatically convert it to integers. And then you'll have to wrap it into JSON number. And it will just work. It will just work. So let's give it a try. If I run parser JSON number on this thing, what will I get? What will I get? I'll get nothing, which is kind of strange. Okay, very interesting, because I probably forgot to reload it. I always forget to reload it. So now it should just work. You see, it parsed the JSON number and it left hello for the rest of the parsers. There we go. But there is one problem. What will happen if we provide empty input? So this read right here makes a wrong assumption that this input will be correct and will be not empty. So this thing may return empty output if there's no digits at all. It doesn't fail if it's not empty. And this is a huge problem. It's a huge problem. So what I want to do is create a parser combinator that takes a parser that parses a list of characters or list of something and returns pretty much the same parser with the same type, but it fails if the initial parser returns null or empty, something like that. I'm gonna call this thing not null. So basically, here's the following idea. We take this parser and we wrap it into another parser. It takes the input, then it, what does it do? It applies that input to the original parser and simply checks, is the result empty or not? If the result empty, we fail the whole parser. If it's not, well, we pass the result on. This is the whole idea. And it doesn't work, as usual. Nothing works the first try because you're supposed to run this parser like that. Not necessarily, we can unwrap it like here, something. Still doesn't work because this thing is supposed to be wrapped in just to indicate that it was successful. Still doesn't work because I forgot a comma. Nice. And now it works. The idea is super simple. We take a parser and we wrap it into another parser that calls the original parser, and if the result is empty, it fails the whole parser. So now we can ensure that this thing is not empty, like that. So now if you provide the empty input, it will say nothing. If you provide something that does not contain digit, it will say nothing. But if you provide something that contains integers, there we go. It has something. So you see this particular, it's sort of a guard. Decorator. Is that what Zoomers call it today? Yes, for Zoomers out there, it's called decorator. We are decorating parser. Now we know how to parse number, which means we can level up our JSON value. So now our JSON value can not only parse nulls, booleans, but also numbers. So hello is unparsable right now, so it will return nothing, but null works, true works, false works, number works. We just leveled up our main parser. So the next thing is going to be implementing string. JSON string parser string. We'll need to utilize a very interesting operations applicative available in applicative. Applicative yet again. Let's take a look at applicative thing. So applicative interface has two very interesting operations. On top of this double penetration, it has half of a double penetration. These things. What these things do? What these things do? Why do we even have those weird directed things? So you see, they accept two applicatives with different types. But the first one returns B and the second one returns A. What's interesting is that you see this one points to the right one and B is the right one and returns B, which is the right one. This one points to the left and returns A, which is the left one. As we know, maybe is an applicative. Maybe is an applicative. There we go. Let's try to apply that operation to maybe. So what's funny is that if you encounter a very weird interface in Haskell, just check if maybe supports that interface by doing :info, right? Because maybe supports a lot of them, like major interfaces here. So that means you can experiment with different operations using maybe. How can we do that? We can use just 5, and let's try this one, just 6. It returns 6. What if we try a different one? It returns 5. Why do we need such operation? Why do we need such operation? Why does it only work on applicatives? Why does it only work on applicatives? We could implement those operations like, I mean, without any applicatives, I could just do things like that and it will work on any type. What's the point of this thing to be applicative? There's just no point. I can do that for any type, just pick the one left one or the right one. Well, applicatives usually have some kind of an inner state that you have to manage. For example, in the case of our parser, you have to keep forwarding the input. So if you're combining two parsers together, that combination is supposed to take the output of the first parser and pass it to the input of the second one. Right. You cannot just easily, combine two parsers together without doing that management, that input management. So if these things were parsers, that will combine these two things into a bigger parser that calls both of them, but returns the value only the one that we chose. So in this particular case, it will apply both of them, but we will return the value only of the second one. And in this case, it will apply both of them, but only return the value of the left one. So you see, you can chain several parsers together and then point out to the value of which you want to return. And that actually leads to a very interesting code. For example, let's imagine that, let's do the following thing. I can do something like, I expect JSON string to start with quote. Then I say that it's gonna end with a quote as well. And between the quotes, I expect a string literal of some sort. Yeah, something like that. So you see, basically it will make sure that it starts with a quote, but it will throw it away. Then it will make sure that then it goes string literal, and it will remember it, and then it will make sure that it ends with the quote, but it will throw it away. So you can sort of point to the value that you want to return, and this and the type of this entire expression is going to be the type of this particular thing, which is quite convenient. So the question is, what's going to be the string literal? String literal. Well, since the termination character is quote, the string literal is going to be everything that is not quote. So until it's not quote. That's it. Almost. What's the problem here? What's the problem here? It doesn't support escaping. Supporting escaping is actually will probably make today's stream even longer, so I decided to put it into the same category as integers. Because yeah, I think we don't really have time to consider like supporting floats, so we support on the integers. And in case of strings, to simplify explanation, I think we're not going to support escapes. So we're going to just support it like that. So, and again, the code is going to be published. And feel free to add an escaping support. No escape support. Furthermore, JSON string, by the way, is supposed to return JSON value, right? So, which means that we'll have to take the whole expression here and penetrate it and wrap it into a JSON string like that. And now it will just work. And since we have a JSON string, we level up our JSON value and add support for JSON strings. You know what's interesting is that when we only started, it was actually quite painful to implement these small parsers. Like, remember how much time we spent on implementing null and how much spent we implementing Boolean and so on and so forth. But as we implement more and more tools to combine parsers together, it actually becomes easier and easier, because now string is super easy. You just combine 3 parsers together and that's it, because we already have all the tools in place. So, and it's gonna become even faster starting from that, because the next type after the string is array. So how do we parse arrays? Well, I think array is not going to be faster, but after we implemented array, the object is going to be super fast. JSON array, right? JSON array, JSON value actually, in fact. So what is a JSON array? It's a sequence of JSON values surrounded by braces and separated by commas. Okay. So if it's surrounded by braces, we have to use our old trick that we did in the string literal. So we're gonna put it like that. And here, somewhere here, we expect elements. So you see, it's elements surrounded by braces. Elements surrounded by braces. So, but the question is, what is elements? What is elements? Yep. What is elements? Well, elements is JSON values, and we already know how to parse JSON values. Here it is. So we already know how to parse JSON values. You see, when we introduced JSON array, the type instantly became recursive. And once we started to implement JSON array parser, the implementation also starts to become recursive, because to implement JSON array, I need to refer to JSON value, and JSON value in turn will also refer to JSON array. So you see, it becomes recursive. Okay, so elements are separated by commas. So we need to know how to parse the separator. So what is a separator? It's just a comma, right? It's just a comma. But what's interesting is that comma can be surrounded by white spaces. Comma can be surrounded by white spaces. What is a white space? Well, it's this. So we already have a function that, you know, parses characters by their category, and which help us to do the following thing. So separator is a bunch of spaces, comma, comma, a bunch of spaces. So what's interesting is that white spaces is such a common parser that it would make sense to extract it to a separate name here somewhere. String, and just implement it like that. So you see, it's a little bit easier to read now. So separator is a bunch of white spaces, comma, a bunch of white spaces. So usually when we work with parser combinators, we have a following operation called sep by that combines two parsers. So it takes a parser A and parser B and returns a parser of list of B. So what it does, it combines them together in the following fashion. The first one is used as a separator and the second one is used as an element. So yeah. So the only thing we'll have to do is to implement such thing. Just send it without white spaces, lol. Yeah, that's exactly how we do that. Anyway, so elements is going to be just sep by sep JSON value. So JSON values separated by separator. Maybe it would make sense to actually, you know, inline that so it looks a little bit better. Yeah. So elements is JSON values separated by commas with white spaces surrounding them. Something like that. Doesn't compile for some reason. Why it doesn't compile? Because this thing is supposed to return. Yeah, this one is interesting. This thing will return a list of JSON values, but this parser expects a single JSON value. This is because you need to take this entire thing and actually penetrate it and wrap the inner value with JSON array. That's it, and that will just work. But the problem here is that we don't have this particular thing implemented yet. So we take a single element, a separator, and how do we implement that? So the first thing is supposed to be an element, right? And then we have to have a bunch of elements. So how can we describe a bunch of elements? So we have a single parser. How can we convert it into a list of parsers? It's a wrong actual question. So we have parser B, and we need to make a parser that returns a list of these Bs. What's interesting is that if you take a look at the alternative implementation, I want you to do info. It has a function menu that takes alternative of A and returns alternative of list of A. Interesting, is it not? What about the spaces around the braces? Yeah, I think it does make sense. Thank you. It's a valid concern. We can just include them like that. Yeah. I think I just forgot about them. I don't know how to would be better to align them, but yeah. Yeah, thank you. Something like that. Okay, so we'll compile. We have not implemented JSON array, I think. Okay, cool. So you see, this thing takes a single one, but returns many of them. So, for example, imagine that you have parser that parses null, JSON null, and you have the following string. What that will return? Well, that will parse only a single null and leave everything, you know, for the next of the parsers, for the rest of the parsers. But if you apply many to this thing, it will actually parse all of them. So basically what it will do, it will apply the parser until it fails, and then will return you the list of the things they parsed. So this function just applies as long as it can. Once it fails, it will return the result it collected. How it works? Since it's alternative, it knows what is an empty alternative, and failed parser is empty alternative. So this implementation of this operation knows when to stop. It knows when to stop. So, and this is something that we can use here. So if you want several elements, you can just apply many to them. So that will parse several elements. But this is a little bit complex because we need to take into account how they are separated. So I usually go the following way. So the parser starts with elements, right? The parser starts with element. Then I have many elements that start with the separator, and we discard the separator. So we have these two parsers. And now I need to combine them together. How can I combine them together? Well, this returns a single element, and this returns a list of elements. I can use the double penetration operation here, and I can penetrate it like that with a const separator, and that will combine all of that into a single list. But that creates a very interesting problem that this sep by does not support empty elements. It does not support empty elements. It's quite easy to fix. You say parse that or nothing, right? So I'm probably gonna even demonstrate you what why exactly that is a problem. Let's come up with the input a, right? And let's try to parse it. Let's rebuild everything. Let's try to parse it like that. What we want to do, we want to separate by commas a. So a is the element and comma is a separator. And we got a list of a's. So string is a list of a's. Okay, let me do the following thing. I'm gonna also penetrate. The problem is that it's a list of characters, but Haskell prints it as a string literal, which doesn't look good. So I'm gonna penetrate it and apply ORD to it. So now it's a list of numbers. You can clearly see that. So if you forget something here, it will not parse. Well, it parsed until it encountered a known character, and it put that character to the rest of the input for the rest of the parser. And it just parses several of them. And what's funny here is that it failed here. No, it didn't fail here. It actually parsed all of them. And if you have one A, it will also parse A. But if you have an empty input, it's incapable of parsing it. So we want to have an empty input to be a valid input, right? And when you structure your implementation like that, you basically expect at least one element. One of the solutions that I found is to just use alternative operation or empty. And that actually solves that problem. So now if you fail on empty, you just return an empty list. But if you have something, you return that, and so on and so forth. So this is one of the ways to implement sep by. And that should implement the JSON array. Believe it or not, that should implement the JSON array. So if we run JSON array and we'll try to apply it to nothing, it will return you an empty array. So what we can put here? We can put null here, and now you have an array with a single element that is null. We can put true here, and now you have an array with a null and true. How about false? We support that. How about numbers? We support that. How about strings? We support that. How about nested arrays? We support that. This is a valid JSON expression, and we know how to parse it. We actually know how to parse it. How about that? So the only thing that is left to implement is a JSON object. Let's go ahead and do that, boys and girls. Let's go ahead and do that. The last one. JSON object. Parser JSON value. What is a JSON object? Well, we know that it's surrounded with curly braces. So let's actually encode that. It's surrounded with curly braces. It's also surrounded by white spaces, that's for sure. So what do we have inside of the object? So this is just a boilerplate around the object. What's inside of the object? Well, inside of the object we have pairs, right? Pairs of keys and values. Keys and value, key and value, key and value. What is pairs? Pairs is basically a single pair separated by a colon. Separated a colon by colon. And what is a colon? Colon is surrounded by white spaces. No. It's my God. It's separated by comma, not colon. I'm sorry. Yeah. Pairs are separated by commas. Yeah. Can I actually make it a little bit more readable? Is it possible to make it more readable? Okay. So we expect open curly braces, then white space, then pairs separated by commas, then more white spaces, then closing curly brace. Everything seems okay, except we don't know what is a pair. We don't know what is a pair. Well, pair is a thing. It's basically a string literal, if I remember correctly, then a bunch of white spaces, then colon, then more white spaces, then JSON value. Am I correct here? Did I not miss anything? I think I'm correct here. String literal, a bunch of white spaces, colon, a bunch of white spaces, JSON value. I think that's what it is. It's actually JSON string JSON value. Not really. It depends. The problem here is that the type that JSON object is capable of holding is string JSON value, right? That means it would be easier to parse it as a string, not JSON string. And we don't have type JSON string. There is no such type. JSON string here is not a type. It's a data constructor for the type JSON value. JSON string is not a type. It constructs a value of a type JSON value. We can't have JSON string as a value here, because there's no such type. So that's why we have to work with the string literal. This is why. So set by first one is a separator. Okay, everything seems to be okay. Okay, let's see if it compiles or not. It does not compile because, again, this one is a little bit more complicated. What's fun is that we cannot really simply redirect everything. These redirection operators work great only if you have to extract a single value. But here we in fact need to extract two values. We need to extract two of them. So what can we do here? I'm just thinking, what can we do here? Well, we can I think we can use the double penetration thing here, but the separator itself is going to be like a separate thing, right? It's going to be a separate thing. So which creates a single applicative to which we have to apply a function of 3 arguments. To which we have to apply the function of 3 arguments, A, B, and C. Something like that. Let me see. Yeah. So A in this particular situation is going to be equal to string literal, B is going to be equal to string separator, and C is going to be equal to JSON value. So the first one is a key, third one is a value, and the second one is going to be ignored. And what we'll have to do, we have to just combine them into a pair. That's pretty much it, and see if it compiles. It does not properly compile because we have a possibly incorrect indentation, and indentation is always painful in Haskell. I never know how properly indent things, so I'm going to just straighten everything up. Still doesn't work because probably I have to... Yes, this is what it expects from me. Okay, so we managed to do all of that. So, but the problem is this entire expression actually returns a list of pairs, but we expect JSON value, which means, again, we need to take this entire thing, penetrate it, and wrap it into JSON object. Just like that, and it compiles, and we're gonna level up our JSON value parser into JSON object, and suddenly our JSON value supports the whole JSON. It just does. Let's see if it works or not. So now we have an array, we have a pretty big array. What if inside of array we would have like an empty object? And it couldn't parse it. Nice! Because I have forgot to rebuild the thing. Okay, here we go. So I'm not sure if it's visible or not, but I'm gonna put my camera somewhere here. So empty object, JSON null, JSON Boolean, true, false, 34, test, and so on and so forth. What if we add values to this particular thing? Foo, I'm gonna have foo, 42. Yeah, something went terribly wrong. I wonder what I forgot. I wonder what I forgot. So this thing is separated by commas. So this is a pair. I have no idea. So let's actually troubleshoot it specifically on JSON object. So let's just put it here and see JSON object is incapable of parsing that. But if we put thing here, excuse me, still nothing. But it's capable of parsing just an empty one, just an empty object. Regardless of the amount of spaces, it's capable of parsing empty object. So which means that the problem somewhere in this particular code. Maybe in here, or maybe in the pair definition. So we expect a string literal here. Oh, wait a second. I know what's up. I know what's up. String literal actually does not include double quotes. That's right. So basically, my God. So this is how it has to be. String literal should include quotes. And after that, this thing should work. Still doesn't work. Now string literal is recursive. Ah, yes, that's right. I'm already tired, I'm really sorry. Span p not equal to, yes, not equal to what? To, yes, thank you so much. Yes. Yes. Yeah. I'm really sorry. I'm really sorry. It should work now. It should work now. See, it works now. Yeah. By the end of the explanation, I'm already super tired, but at least we have a full JSON parser. Thank you so much, chat. Thank you so much for support and helping me to troubleshoot all this stuff. But we have the full parser under 111 lines of code. Without any third-party dependencies. Without any third-party dependencies, only base. We know how to parse the whole JSON. Well, there are nodes here and there for escape support, for proper error handling, maybe for support floats, but overall, it's actually a legitimate JSON parser. And furthermore, let's actually test that on a real data and see how it's going to work. So I have a schedule page. You can check out the schedule page here. And what's interesting specifically about schedule page is that it makes a query to schedule.json and downloads JSON data from the website and just builds the schedule based on that JSON. It's a pretty big JSON, not that big, but I mean, it's pretty involved. Let's try to parse that JSON using our parser. Can our parser parse this mess? This is like a valid JSON. Can our parser do that? Let's find out. Let's actually find out. Let's wget that JSON. Okay. The problem with this JSON specifically is that it has escaped quotes. It's not really a great thing, but let's help our parser a little bit and just remove these escaped quotes and pretend that never happened. Our parser just does not support them specifically. It just doesn't support them specifically. But overall, it should be able to parse this thing. Let's implement a helper function, which will be called parse file. It will take a file path and probably parser A, and it's supposed to return, I think, let me see, IO, maybe A. Yeah, basically it accepts the file that you want to parse, the parser with which you want to parse the file, and then it returns the result. So what do? We want to read the file. Yes. We read the file and we read it into the input. There we go. Then we just run parser on the input, and we get maybe the rest of the input and the actual parsed result. So what we need to do here is actually discard the rest of the input, because as you can see, parser returns this string and we don't really care about it. We need to take the second element inside of maybe. To take a second element inside of something, you are doing what? You're penetrating and you're grabbing the second one. And after that you just return all of this stuff. It works. So now we have a function that is capable of applying parser to a file. Schedule JSON is here. Let's parse, let's reload everything. Parse file, schedule JSON, and what we parse in JSON value. There we go. It actually parsed JSON. Our parser that we implemented from scratch without using any third-party dependencies, like slightly over 100 lines of code, parsed the JSON that is used in production by our schedule page. Well, we had to remove escaping, but I mean, it's just to keep the stream concise. Because we're already over 2 hours, and I wanted the stream to be pretty short. But it actually managed to parse it. Look at that. So you have JSON array, you have JSON object projects, right? You have JSON object projects. Then you have all of the projects and so on and so forth. Maybe we want to extract some kind of a data from it. What do you guys think? For example, I don't even know what we can extract there. So it has to be just, we can try to pattern matching, I suppose. So this thing is supposed to be just, then the value JSON object, and it's supposed to be a list. And I think we can do something like that. So it's going to be JSON object. First element of the JSON object doesn't even work. I don't know what exactly wrong here, but oh, it has to be head. So we take the first element of JSON object. What do we have here? We have projects, and yeah, maybe it would make sense to take the second element of this thing, which the projects themselves, and what do we do here? What do they contain? It's an array, so we'll have to assign it to JSON array wise, which will contain all of them, wise, and hopefully we can map them. Yeah, we'll see. We're slowly extracting them. I want to extract the names of the projects that we have. slowly extract the names of the project that we have. But it's kind of painful because they are objects, but we can do something like map, then JSON object. I'm not sure if I can do that. And then I have access, and I think I can look it up. I'm pretty sure I can look it up. Google lookup. And yeah, I should be able to do that. So it actually works with associative lists. So I want to look up a name, right? I want to look up a name on access. Will that work? It doesn't work because I probably have to do something like that. And yes, there we go. Here are all of the names that we have here. Maybe I can do something like print. And basically, I just extracted all of the names of the project that I in my schedule, the current one and the past one. And I extracted that information using our parser that I implemented from scratch. Yes, I extracted that information, Jesus Christ, from this website, from this JSON. Where is PogChamp in the chat? My God. I'm showing you this epic stuff and everybody's silent. What the hell is going on? See, we parsed this shit from scratch in Haskell. Where is PogChamp? There we go. My God. I'm disappointed. And we extracted that information. Anyways. This is what I wanted to make a YouTube video about. But as you can see, it's kind of difficult to make a video about that very concise. It's kind of difficult to do a very concise video about all of that, because as you can see, you need to explain a lot of interesting things like functors, applicative alternatives, how we combine all that together, and so on and so forth. And yeah, this is why I decided to make a stream where I will share that content, and so hopefully that content will not be wasted. Maybe you learned something new today, maybe you're disgusted by all of this intellectual masturbation and you will never program in Haskell again. In any case, I'm really happy you enjoyed the content. So today is supposed to be day off, but I still wanted to do that stream anyway. Thanks everyone who's watching me right now. I'm gonna publish, by the way, no, let's not go anywhere. Let's publish this shite. I'm gonna do git init. Git init, I initialized this stuff. Ready, set, go. Will negative and exponential numbers work? No, they won't. And you apparently missed the beginning of the stream where I addressed that specific question. Tesla, go back and watch again. So let's create the repo, and I'm gonna upload all of this stuff. Maybe I want to go somewhere here. Wait a second. I saw this pattern before in Elm, but never implemented. Yeah, it's actually like what's funny. Okay, I got derailed, slightly derailed again. No, not history. Hackage. Usually when people think about parser combinators, they think about parsec, right? So you can use this kind of thing. So people implemented that idea multiple times, and in majority of the cases, you just want to use the existing implementation. But because of that, people forget that it's not that difficult to implement your own parser combinators. It's actually super simple. This implementation probably not as fast as this one, but if you want to parse something simple and don't want to depend on a huge third-party dependency, and this third-party dependency is quite big, like it depends on other things, MTL especially, which depends on other things in turn. You just want to quickly parse something, you can implement all of that yourself. So yeah, okay, let's create a repo. Haskell JSON, there we go. I'm gonna grab the origin. I'm gonna add origin here, boom. And let's push that right into the repo. And if we refresh that, so all of the source code that I've written live on the stream is available right here, right now, right here, right now. So you can play with it. And yeah, the vote of this stream is actually a proof that implemented all of that live from scratch. What's funny is that I didn't even have any script. I just followed my thought process several times already, and I kind of know how to implement this thing. So in any case, I hope today's stream was useful. Maybe you learned something, maybe not.